So this is chapter 20 quiz. Okay, the first one. Two 3.0 microcoulomb charges lying on the x-axis, one at the origin and the other 2 meter. Okay, so this is 0, this is 2.0 meter, and 3.0 microcoulomb, and 3.0 microcoulomb, right? So here and here, 3.0 microcoulomb. All right. What is the potential relative to those charges at point 6.0 on the axis? Okay, so you have two point charges, right? So I ask you about here, 6.0 meter. What's the potential here at this location? All right, so we know potential due to point charge. So V, potential due to point charge, equal to K, Q, R. Okay, and well, you have 2 point charges. Then what's the potential there? Potential at this location, right, equal to, use this equation, calculate the potential due to each charge, and then add them together, right? So potential due to Q1 is Q2, right? Due to Q1 is Q 3.0 microcoulomb times 10 to the negative 6 distance, right? So this is 0, this is 6, right? 6. All right. And then potential due to second charge, K 3.0 times 10 to the negative 6. What's the distance from here to here? 4 meter. Okay, so that's it. So this is, so you put 8.99 10 to, same thing here, 8.99 times 10 to the power 9. Okay, so just a good calculation. That's the potential. All right. So potential, net potential due to point charges is due to 1 point charge, use this equation. So now you have a 2 point charge, right? So basically potential V equal to V1 plus V2. So this is potential due to the for Q1 plus potential due to Q2. All right. Second one. Okay, second. A proton that is initial at rest is accelerated through electric potential difference. So we know delta V equal to 500 volts. Okay, how much kinetic energy does it gain? All right, so you see proton is a charged particle. Okay, so charged particle moving inside of the electric field. What you have here is energy conservation. Energy conservation gives us delta KE plus delta U is 0, right? Okay. So delta KE start from rest, right? So KE final minus K. So ask you about how much kinetic energy does it gain. Okay, so basically ask change of kinetic energy, right? Equal to negative delta U, right? Equal to negative Q delta V. We know delta V is 500, okay? And Q is 1.6, right, proton. So this equal to negative 1.6 times 10 to the 19 times 500. Okay, so this is negative, right, which means change of potential is negative. Potential energy drop by whatever value here, and this guy gain, okay, same amount of this, right? Okay, so so the answer will be this times 500. Okay, potential energy drop. This guy drop certain value, and then this guy gain. Okay, same amount. All right, number 3. Proton with a speed of this. A proton with a speed of, this is speed, meter per second, accelerates through a potential difference and thereby increases speed. So this is V I, VF equal to 4.0 times 10 to the power of 5, right? Meter per second. Through what magnitude potential difference did the proton accelerate? Okay, so we still use energy conservation, right? Delta KE plus delta U is 0. Okay, so ask you about through the magnitude of it. So you can tell if this guy increase, right, this guy got to decrease. Okay, so you look at delta K equal to 1/2 m VF squared minus 1/2 m VI squared, right? So plus Q, it's a proton. Proton Q is 1.6 times 10 to the negative 19. Delta V is 0. Okay, so we can figure out delta V. So here, VI is 2 times 10 to the power 5, 4 times 10 to the 5, right? Mass is, proton is 1.67 times 10 to the negative 27. Okay, so you know mass. So the whole equation, this is unknown. Delta V is unknown. Okay, so just like figure out delta V. And here, delta V got to be a negative value, right? They're looking for magnitude. Okay, so you just answer, your answer will be just put a positive value there. Okay, because you're looking for magnitude. All right, number 4. Oh, by the way, the calculation can be a little bit messy here. Just be patient. Use your calculator. Number 4, 5.0 micron Faraday capacitor has a potential difference. So see, so C equal to 5.0 times 10 to the negative 6 Faraday. Potential difference V equal to 5.0 volts. Apply across its place. If the potential difference across plates is increased to 8, so V1, V2 equal to 8.0 volts, how much additional energy does the capacitor store? All right, so we know capacitor store energy U equal to 1/2 CV square, right? Okay, so we know U1 stored energy equal to 1/2 C V1 square, right? And then if you increase the potential into V2, right? So U2 equal to 1/2, capacity the same, right? It solely only increase the voltage, right? V2 square, and ask you how much additional energy does the capacitor store? Additional, looking for change, right? So V2, U2 divided by minus U1. So that is additional energy stored by capacitor if you increase voltage from 5 to 8 volts, all right? Just plug in, right? So for example, U1 equal to 1/2 5 times 10 to 6, right? And then V square, 25 square. So this one is the same thing. 60, no, so 5 square equals 25. So 8 square equals 64, right? So you do the subtraction, okay? All right, number 5. Okay, a capacitor has a voltage of, so voltage is 391 volts. Apply across its place, and then the voltage source is removed. Okay, so what happened here is this is a capacitor, right? And then this is the voltage source. And you connect, right? So this is like that. Then what you do here is you remove this. Okay, so when you put a voltage here, you put a charge, you trap the charge here. When you take this guy away, but the charge is still there. Okay, so it's a trapped charge. Okay, the charge can go nowhere. Just like it's a trapped. All right. So what is the potential difference across the plate if the space between them is then filled with mica? Okay, so what happens here? You trap the charge, right? Then you put mica inside, right? Okay, so So how to solve this kind of problem? So first, look at what is the charge you trapped here, right? So, okay, so this is, assume at this moment, capacitance is C, right? So Q equal to CV, all right? And then this is C times 391. That's the amount of charge you trapped, right? And then you put a marker here. So by putting marker, so C prime equal to 4, it's 5.4, right? 5.4 C. So slowly, just simply put a marker here, you increase capacitance by this much. Then voltage equal to trapped charge divided by capacitance. This amount of charge is the same, right? So amount of charge equal to C 391. Okay, C prime equal to 5.4 C. Okay, C and C cancelled. And so this is amount of charge. This is the potential difference. Potential difference will be decreased. All right. So by 5, what? It's about 72 volts. Okay, so this is a logic here. You, by cutting off this voltage source, you trap the charge here. Okay, charge can go nowhere. And then if you put this, right, so, potential voltage will decrease. All right, number 6. Number 6 here is, okay, number 6. A uniform electric field has strength. Okay, so E has 7.0 Newton per Coulomb. What is the electric energy density? Okay, energy density. Okay, just appear from equation. Energy density equal to lowercase u 1/2 epsilon naught E square. Just this equation. Okay, just this equation. Plug in, you see, you give your epsilon naught, right? E square half, and you calculate that. All right, number 7. A small charge is 4.0, right? So Q equal to a small 4.0 microcoulomb charge and a small 1.5 microcoulomb charge are initially very far apart. Okay, they are very far apart. Okay, so Q1, Q2, 1.4 microcoulomb. How much work does it take to bring them to a final configuration? Okay, so final configuration here is this. Q1 is, so x-axis, right? So Q1, so this is at 1.0 millimeter. Okay, so bring to final configuration, which 4.0 is at 1.0, y is 1.0. Okay, so this is, actually you have, this is 1.0. So here is your Q1, right? And 1.0, 3.0. Okay, so 1.0, 3.0. Okay, so this is Q2. Okay, so what's work done? All right, so here we have to use this way. So work done, right? To put this final configuration, work done, right? So what's total work done? Work done equal to potential energy held by this system. Okay, potential energy held by this system, right? So what's the current energy held by this system? Okay, so in class we talk about this, how to calculate potential energy held by, you see, Q1, Q2, two charges, right? Separated by distance r. All right, so at this configuration, potential energy is K, Q1, Q2, R. All right. Separation is R, right? And Q1, Q2. Okay. So here, so you see Q1 here, Q2 here. What's the separation? Separation here is 2 millimeter, right? Okay, so 2 times 10 to the negative 3 meter. That's a separation. You see separation. Okay, so because this is a 1, 1 and 1, 3, right? Okay, so plug into this equation. Q1, Q2, K, right? K is 8.99 times 10 to the power 9. Okay, separation is 2 times negative 5, negative 3, all right? So just like whatever it is, plug in. Number 8. Okay, number 8. An ideal parallel plate capacitor having circular plates of diameter D. All right, circular plates, right? Diameter D, right? Circular plates. Diameter D. So diameter D. That are distance lowercase d, right? So you see one, another one, lowercase d separation. Stores U when it is connected across a fixed potential difference, right? So basically you have this one, right? Connected to a fixed potential difference. Okay. If you want to triple the amount of charge stored in this capacitor by changing only the size of its plates, the diameter should be changed too. Okay, so all right, so this is a fix, right? So energy stored will be 1/2 C and U equal to 1/2 CV squared. Okay, so here, what's C? C equal to epsilon naught A over D, right? And A, because this is a disk, right? So epsilon naught A equal to pi D over 2 squared divided by separation. All right. So if you want to triple the energy, which means you have to triple the capacitance. Triple the capacitance, you only change the area, right? Okay, so here, so this equal to epsilon naught pi over 4 d squared divided by d, right? You triple this one, you only change the area, which means you have to make the diameter square root big, 3 big. Okay, so this is square equal to 3d square, right? All right, which means you just change the diameter into square root 3d. Okay, make the diameter square root 3 times bigger. All right. Number 9. When a 6.0 microfarad air-filled capacitor has a charge. Okay, so we know you put a charge 40.0 times 10 to the power of negative 6 coulomb on its plate. Well, positive, negative, which means one plate is positive amount of charge, another plate is negative amount of charge. How much potential energy stored in this capacitor? And we know capacitance equal to 6.0 times 10 to the negative 6 Faraday energy, right? So energy here is 1/2. If you know amount of charge, you know capacitance, use this equation, Q squared over C. Okay, so we can figure this out. All right, just plug in and you get it. Number 10, as a proton moves in a direction perpendicular to electric field. So this is electric field. Okay, this direction. Proton move perpendicular. This is a moving direction. Perpendicular. What does it mean? Perpendicular means work is 0, right? Work equal to force displacement cosine angle. Angle here, perpendicular is 90. Cosine 90 is 0, right? Okay, so force equal to QE delta S, right? This is a 0, so work is 0. Okay, so um, so what is ask you about the, it is moving from, okay, so potential difference, right? Delta V equal to delta U over Q, right? Delta U equal to negative negative work done divided by Q, right? So this is work done equal to QE delta S cosine theta divided by Q, right? Q cancelled. So potential difference is negative E delta S cosine, well, perpendicular is 90, right? So this is 0. Okay, which means delta V is 0. Okay, so it is moving, so A is moving from low to high. No. B is moving from low to high. Actually, it's delta V is 0, which means potential energy change is 0. Okay, both is electric potential and the potential energy remain constant. Delta V is 0, delta U is 0, which means potential remain constant and the potential energy remain constant. Okay, so that's an E. All right, so here is your answer. All right, so last one kind of kind of tricky here. Perpendicular is a main word, key word. All right, so that's all for chapter 20 quiz.